Okay, so to answer this question or any of these kind of questions about these various sets, integers, irrational, rational, real, natural, whole, all this kind of stuff, let's look at all these questions come from this kind of a diagram. This is a very nice diagram. Let me talk to you about this diagram and how this works. So let's go through the various kinds of numbers. We'll start up here with the natural numbers. The natural numbers are also called the counting numbers, natural or counting. And so that's just 1, 2, 3, 4, etc. Those are the natural numbers, the ones that you learned when you were first talking about numbers, the ones that came most naturally to you, the ones you count on. They're called the counting numbers as well. Next, I want to mention the whole numbers. So what are the whole numbers? The whole numbers are the ones that, here, let me change the color a little bit. The whole numbers, trying to find an appropriate color here. I'm probably being too picky, whatever. Here, I'll do this. All right, so the whole numbers, all they do is throw in the zero. The way I remember it is they have the whole, they have the number, the zero. So it seems kind of silly to make a whole new name when all it is the same as the counting numbers, just throw in the zero. Now you have the whole, you have the zero. All right, things will get more interesting as we come down to the integers. Does anybody know what are the integers?
Aren't they the numbers that are both positive and negative?
There it is, exactly. That now we throw in the negatives, yeah. -3, -2, -1, 0, 1, 2, 3. So it goes forever, both directions. It includes the negatives. So do you see how these cups are fitting inside of each other? See how the natural numbers fit inside of the whole number cup, which fits inside of the integer cup, right? So integers include the whole numbers, which includes the natural numbers. So if you take a number like 7, it's a natural number, it's a whole number, and it's an integer, isn't it? Because it's in this cup here. And if you're in the natural number cup, you're also in the whole number cup and the integer cup. In fact, you're in the rational and the real number cup as well. We'll get to that in a moment. All right, let's keep going. Now things get more interesting. So now we want to talk about the rational numbers. What are the rational numbers? Let me write them up here. Rational numbers. The word comes from ratio, which means fraction. So it's numbers like 2/3, -5/7. So it's all the fractional numbers. Those are new. Integers don't include fractions, right? No fractions. But the rationals expand it. They include fractions. So even like 8/1, which is really the same as 8, isn't it, is a rational number. So do you see why the rationals actually include the integers? Every one of these integers I could write as a fraction, or I could not. It's optional, right? So therefore, they are also rational numbers. Do you see why I'm explaining why the integers are contained in the rational cup? Because every integer really could be written as a fraction, so it really is a ratio number. All the integers are ratio numbers. These could be written as fractions, 3/1, right? Now, you might be confused, like, yeah, I get that, Mr. But why'd you write no fractions? Well, what I mean is there's other numbers like 2/3 or -5/7 that can only be written as a fraction, cannot be written as an integer. I think you understand. So those are ratios. Now, what about decimals? Well, this includes decimals as well. So if you have numbers like 0.7 What is 0.7? It's 7/10. You know that, huh? We did that whole decimal unit. So 0.7 is also a rational number because it can be written as a ratio. Well, what about like if you have repeating numbers? Like what about 0.7 bar? You know, that's like sevens forever. 7, 7, 7 forever. Right. What did we learn that's equal to? Do you remember? 7/9. It's been a while. You have to review that before the final. Remember, the numbers that go forever can also be written as a ratio. It's over 9. So that's 7/9. So all those decimals, they go forever like that. They here, I'll write equals 7/9. They're ratios. So basically, the answer is it's fractions and decimals. Decimals that end or go forever with a pattern. Or go forever with a pattern. That's really important that you understand that. That's ratio numbers. So all of that is rational numbers. All of this description is rational numbers. So rational numbers are fractions, I'll say or decimals, fractions or decimals, decimals that end or go forever with a pattern, as opposed to irrational numbers. Irrational numbers, those are decimals that go forever with no pattern. That's what makes them different. They go forever with no pattern. Well, what numbers do that? Square root numbers that are not clean, like square root of 2. If you do square root of 2 in your calculator, I'll do it right now, you'll get 1.414. Looks like a pattern, but then it breaks away. 2, 1, 3, 5, 6, 2, and on it goes forever. No pattern. And now, some square roots are clean. Like square root of 3 also is no pattern, right? That'd be 1.73205. On and on, no pattern. But then square root of 4, that's just 2. That's just a whole number. Square root of 4 is just 2. That goes up here, doesn't it? So some square roots, if they're clean, just are whole numbers. But square roots that are not clean, their decimal goes forever with no pattern. They're irrational. And then another example would be pi. You know pi, right? 3.1415926, blah, 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 forever, no pattern. So decimal numbers that go forever with no pattern, those are irrational numbers. They have no pattern. They go forever. So, and then all of these fit inside of the final dish called real numbers. So do you see how they fit inside of each other? All of these are called the real numbers, both the rational ones and the irrational ones. And inside the rational are the integers, the whole numbers, and the natural numbers. Excuse me. Okay, so putting this together then, let's go on up and let's answer some of these questions. So like on number 5, it says negative 67, at least on mine, it says negative 67 belongs to which categories? Negative 67. Well, if I come on down here for negative 67, Negative 67, is that a natural number? No, that it's negative. So no. Is it a whole number? No, it's not a natural or whole. Is it an integer? Yeah, because that's negative numbers. Yeah, negative 67, it's an integer. So negative 67 is right inside of this dish. It's in the integer dish, isn't it? And if it's in the integer dish, then it's also rational because you can write it as a ratio, negative 67 over 1. And of course, it's also a real number because all the integers and rationals, right? The integer dish is contained in the rational, which is contained in the real. It's not irrational, it's not whole, and it's not natural. Does that make sense? Negative 67 is an integer, a rational, and a real because it's predominantly, firstly, in the integer dish, which is in the rational dish, which is in the real number dish. So there it is. So negative 67 is an integer, a rational, and a real. So we come up here and go, oh, negative 67, that's an integer, a rational, and a real. So you would check those 3 boxes for that one. How about for this next one? Square root of 11. Well, you can do it on your calculator, and you'll see it's a crazy decimal that goes forever. 3.31662479. Decimal forever, no pattern. Square root numbers, unless they're perfectly clean, are decimals that go forever with no pattern. So where do we see that on our list? Decimals that go forever with no pattern. Decimals that go forever with no pattern. That's irrational, right? To be rational, you have to have a decimal that ends or goes forever with a pattern, right? Like 0.7 bar, 7's forever, that's 7/9, that's a ratio number. But irrational, not ratio, are decimals that go forever with no pattern. So square root of 11 would be firstly in the irrational dish. Right there, square root of 11 would be right here, firstly in the irrational, but therefore it's also a real number. It's going to be irrational and real because the irrationals are inside the real. Irrational and real. Irrational and real. Number 7, 3.9 bar. You know what that means. The 9s go forever. Decimal forever with a pattern. What does that mean if the decimal goes forever with a pattern? Well, as it says right here, decimals that end or go forever with a pattern like 0.7 bar can be written as a ratio. We learned how to do that in the decimal section, how to change all those forever patterns into fractions. It's a ratio number. It can be written as a ratio, a fraction. So it's rational and it's real because all rationals are inside the real dish. It's rational and it's real. So we'd say, okay, that one is rational and it's real. And then number 8 here, 2/7. Well, that's pretty clearly a ratio number, isn't it? That's a ratio. It's a rational. So 2/7. So 2/7, that is fractions. All the fractions are rationals, and they're all reals. So it's rational, and it's real. Rational and real. Number 9 is pi. We talked about pi, particularly. Pi, I listed pi right here. He's a decimal that goes forever with no pattern. He's irrational. So pi is irrational, and he's also real. He's in both those dishes. So he's irrational, and he's real. And finally, number 10, 7 point, and then it has a bar over the 400. So you know what that means. That's 400, 400 forever. Decimal forever with a pattern. So if it goes forever with a pattern, as we say right here, as we saw right here, fractions or decimals that end or go forever with a pattern, That's ratio. Those are ratio numbers because you got a pattern. You can be written as a ratio, a fraction. So it's rational, and rational is inside real. So that'd be rational and real for that number. So there we go. So here is the key. I'll leave that for you. There's the key to knowing which categories things go into. That'd be a good image to save and print out for yourself for the next exam.